In the name of God, the compassionate, the merciful. Engineering Plasticity, Chapter 2, Stress Analysis, Part 8. In this video, we are going to talk about Morse circle for 3D stress system. Of course, I'm sure that you are familiar with Morse circle in 2 dimensions. Generally, Morse circle is used for graphical representation of a stress transformation and the state of stress on a plane. I will probably put a file for you explaining the 2D stress system, Morse circle for 2D stress system probably, so that if you have forgotten about Morse circle, it will refresh your mind. Now, this equation which I'm showing you in here, in fact, is the equation for the transformation, coordinate transformation for the stress. I have shown you this before. We have driven this relationship in previous slides. Also, normal stresses on a doubly oblique plane in terms of principal stresses is like that. In fact, we have used this equation to obtain this, because on a doubly oblique plane in terms of principal stresses, the shear stresses will be zero. The plane will be such that the shear stress is zero. So we have only normal stresses, and we have shown the normal stresses sigma 1, sigma 2, sigma 3 in here. Also, we have driven this shear stress component, which is that. Now, so therefore we have these two equations. Of course, here I can write, instead of L2 sigma 1, M2 sigma 2, N2 sigma 3, I can write sigma. So I will get tau squared plus sigma squared plus sigma squared, because this is a squared here. So I get tau squared plus sigma squared equal to that. Okay, so you can see from here that we can get the Morse circle, because that will be the equation of a circle. Sigma squared plus tau squared equal to something squared is in fact Morse is an equation of a circle. Now, here sigma 1, sigma 2, and sigma 3 are supposed to be known, and therefore we have to get L, M, and N. In order to do that, we write this equation as well. We have this equation, L squared, M squared, N squared. This is for any cosine ratios. This is true. So we have 3 equations, this one, and this one. So from these 3 equations, we can solve for L, M, N, and then we can draw the Morse circle. So as you can see here, we have these 3 equations, and from these 3 equations, we can get the Morse circle, because as I said, if I put here and there, put sigma, I get sigma squared, transfer it over there, we get sigma squared plus tau squared equal to that, and we could get L squared, M squared, N squared, and put it there. Now, in order to do that, I will substitute for M squared in terms of L squared and N squared. And as you can see, we could substitute here so that we get this equation. Sigma is equal to sigma 1 L squared, sigma 2, instead of M squared, I've written that 1 minus L squared, N squared, put it in the parentheses there, and then I could get N squared here in terms of L squared. So as you can see here, M squared is in terms of L squared, N squared. Here I've got only L squared and S squared, so here I get N squared in terms of L squared. Other terms are known, because I said sigma 1, sigma 2, sigma 3 are known, and sigma also is, we will draw the Morse circle to find out. Okay, so I could also substitute for m squared in here, so that I get tau squared equal to, instead of that, I put 1 minus L squared n squared, and instead of that, I put 1 minus L squared n squared. If I rearrange these, I will get this equation, okay? You can see in this equation, I've got L squared, n squared, and so I've got these equations now. I put, instead of n squared, I put here, so that I get everything in terms of L squared in here and there. If I put substitute for n squared, I will get L squared in terms of sigma tau and sigma 1, sigma 2, sigma 3. Therefore, L squared is known. Similarly, I could obtain m squared and n squared. Okay, so I get Lmn in terms of principal stresses. Right then, if I multiply L squared by this, I will get this equation: tau squared plus that is equal to L squared times that. Okay. As you can see, I get this term, which has a sigma squared, and this term tau squared, and this is also the constant. Okay, so I've got sigma squared to tau squared. Also, this is a number, sigma minus a number, constant, and that's a constant. So I get, of course, L is not constant. Okay, L is not constant because L is the cosine ratio, and the cosine ratio can change depending on the angle. If this is cos alpha, then alpha changes between 0 and 90. Therefore, this term changes. So we'll see what happens. Anyway, this is equation of a family of circles because of this L here. Because if this L, if it was constant, then we would have one circle only. But because it's changing, this is changing. So the center of this family of circles is, it would be 0, 0, but it's not 0, 0 because we have this minus this number. So center will be there, okay, on the x-axis, because as you know, the more circle, we have the x-axis is the sigma, and y-axis is tau. So tau is 0 in here, and we got x equal to, sigma is equal to sigma 2 minus 3 divided by 2. So we don't start at the origin. The center of the circle is not on the origin. Right. And the radius is this. Now this radius is not constant because L is changing between 0 and 1. Cos 0 is 1 and cos 90 is 0. Okay, between 1 and 0 it changes. Now since here we solved for this equation, we could similarly solve for the other equations as well. I mean, we got here L squared like that, m squared like that, and n squared like that. So here we multiply this by that equal to that. Here we can multiply this. So we can get similar equations like this one for m squared and n squared, and then from those we could get similar equations like this. We could get the center and the radius. So I'm going to show you this. So this is the one for m squared. The center is sigma 1 plus sigma 3 divided by 2. I have shown this with O C1. O is the origin, C1 is the center. And then the radius will be that, so that if m changes, this radius changes, and here we get m is equal to 0, r becomes sigma 1 minus 3 divided by 2. If you put m here, that 0, m 0, that becomes 0, and you get this. So it comes out of the root squared, and we get sigma 1 minus sigma 3 divided by 2. Similarly, if we put m equal to 1 and rearrange these, we get that. We get r equal to half sigma 1 plus sigma 3 minus sigma 2. If you square that, you will get this under the root, square root. Okay, so this is for one set of circles, and the circles change, the radius changes. Okay, and I will show you how these circles change in a bit. And you can see here also for n squared we get this relationship. All this relationship we got it from previous slide where we had the L squared, M squared, N squared relationships. We obtained those relationships. So we multiply the denominator by the M squared and we put it equal to the numerator. So here also we get N squared and the center is OCT, and because of this we got center there, and the radius is that one. Okay, it's very similar, but of course the sigmas are changed. And if you put n equal to 0, that becomes 0. We get sigma 2 minus sigma 1 divided by 2. And if we put n equal to 1, then rearrange these and we get this. Okay. Similarly, we get OC3 for this relationship, and the radius L equal to 0 radius becomes equal to that, and L equal to 1 radius becomes that, right? So these are we find out how the Mohr circle for 3 dimensions, the relationships are, and we can draw the Mohr circle. That's what we do here. Of course, this sigma 1, sigma 2, sigma 3 in this case are known, because they belong to a third degree equation which we obtained before. So you have to solve that third degree equation to get sigma 1, sigma 2, sigma 3. You cannot find sigma 1, sigma 2, sigma 3 from the Mohr circle. It's the other way around. So we have these are known. So we put sigma 1 equal to OP1, sigma 2 equal to OP2, and sigma 3 is equal to OP3. And we draw a circle, center C1, which goes through P1 and P3, because that is sigma 1. The radius is sigma 1 minus sigma 3 divided by 2. And OC1, that is the coordinate of C1, is sigma 1 plus sigma 3 divided by 2, because the radius is sigma 1 minus sigma 3 divided by 2. That is the radius from here to there, and from here to there is sigma 3. So sigma 1 minus sigma 3 divided by 2 plus sigma 3 gives you this. And also the radius from the previous page was that, okay, depending on m is equal to 0 or equal to 1. So in here, if we put m equal to 0, we get the radius P1, P3 divided by 2, which is this circle. And if we put m equal to 1, we get C1, P2, which is a smaller circle. Okay, so I'll just show you these circles here. As you can see, from this circle we go to that circle as we change from 0 to 1. So that's how it changes. Okay, that is 0, that's 1, and these circles are in between. Okay, so that's how these circles for sigma 1 change from, as we change the cosine ratio m from 0 to 1. And For the second circle, of course, for the second circle, which is sigma 2, we have sigma 1 minus sigma 2 divided by 2 is C2, P2, and the coordinate OC2 obviously should be, this sigma 2 should be added to it, so we get sigma 1 plus sigma 2 divided by 2. And from the previous slide, we had R equal to that relationship. Here is times n squared. So if we change n from 0 to 1, we get these two values, okay, two different values, and the radius changes like that. So if we put n equal to 0, we get this one, and if we put n equal to 1, we get a bigger circle. In the previous slide, our circle reduced in radius. Here it's increased in radius, okay? It's increased from that to that, okay? So the changes are like this. You can see we have a smaller circle for n equal to 0, and the maximum size of the circle when n is equal to 1. And these are in between. For instance, 0.2, 0.4, 0.6, 0.5. And for the third circle, obviously, we have this one, which is sigma 3, centered at C3, and the distance is sigma 3, and the radius is sigma 2 minus sigma 3 divided by 2 plus sigma 3 gives you the coordinate OC3. Therefore, the radius, of course, we had it from before, this relationship is times L squared, and if we put L equal to 0, we get this relationship, and if we put L equal to 1, we get that. So this relationship is with a smaller circle like that, and this is for the bigger circle, which is this, very much bigger circle. So the changes here are like this. As you can see, the circle grows as we change the value of L from 0 to 1, and we get something like this. Okay, so I have tried to show you here that how the this W oblique plane changes, because the circles are related to this plane. In fact, circle is showing this plane. Okay, so as alpha, beta, gamma, or LMN change, if we change from here to there, so the normal changes from n to that, and we get different circles, okay? And so that's how it changes. As you know, in the Mohr circle, we have twice the angles. For instance, if the angle here is alpha, in the Mohr circle is 2 alpha, because in here we have the planes 90 degrees to each other, and in the Mohr circle we have it 180 degrees. In fact, all the sigma is on one plane, but here the sigmas are perpendicular to each other. Sigma 1, 2, 3 are perpendicular to these planes, so perpendicular to each other. But on the Mohr circle, they are on one line. So it means this 90 degree has transformed to 180 degrees. So if we have an angle here, we have it twice that angle over there. Now, we want to know how we draw alpha, beta, and gamma. So alpha here, because what are we doing now is to find out the state of stress, because the Mohr circle, as we showed in here anywhere, let's go back to the original equations here. These Mohr circles, for instance, the first one for sigma 1 is like that. So we said that if we put m different values, we get different circles, but here obviously if we get m a certain value, then sigma 1, sigma 2, and sigma 3 are known, and from the Mohr circle we can find sigma and 2. And now we are going to show how to find these. Okay, so I'll just go ahead here. Now in order to do that, of course, before in previous slide I showed you that, for instance, this circle is for m equal to 0, for instance, okay, or m equal to 1. For this case is m equal to 1. But here I'm showing you different circles. I'm just showing you this m is not 1 because alpha is not 0, okay? Alpha is has an angle. So we are supposing these circles are for element assuming certain values. Now, supposing we have alpha here in general, and then how do we draw alpha? We draw a line tangent to the sigma 1 circle, and we draw a line with an angle alpha. This intersects these two circles. This circle as Q2 and this circle at Q1. And then what I do is that I draw a circle with the radius C3Q2, C3Q1. Okay, that circle. And then that is the circle Q1, Q2, that's the arc. And then I draw another angle which is beta, of course, here because we have this line perpendicular to sigma 2 and sigma 3. I could draw two lines here like that with the beta, which is cos beta is equal to m. Cos alpha was equal to L, cos beta is equal to m. And this is again a certain value of beta. We are drawing these circles. Forget about the previous slides. And so here I draw these two lines with beta angle, and it intersects this circle at R1 and this circle at R2. Then with the center C1, I can draw these two lines. You can see here why this is so, because this center C1 is for the sigma 1 circle, and here we have put this m, this cos beta is m. And if you remember in our derivations also, the equations that we draw this circle from was the relationship for m2. In fact, here also is for m. Also here the relationship was for n2, and also this is L2. Sorry, the relationship was for L2, and we have drawn with the center C3. C3 was for sigma 3. If you go back and have a look at those relationships, you can see a logical relation between those equations and what are we doing here. Okay, here we have R1, R2, and Q1, Q2, the two arcs that meet at this point. This point of intersection, in fact, is the state of stress. To illustrate this further, we could draw the third line as well. So from center here, we draw a line to S2, and from this center, we draw a line to S1. And if we pass an arc through S1, S2, it should pass through this point. And that's what we do, like that. That's arc S1, S2 goes through that point. So that is the point of intersection of three arcs, which are related to L, M, and N, as shown in the previous slides in those equations, L squared, M squared, N squared. Therefore, this is the point of intersection of these three arcs, and that's the point which shows the state of stress. And therefore, if we drop this perpendicular here, perpendicular there, we can get the stresses. That is the shear stress, and that's the normal stress, okay, sigma and tau. So that's how we draw the Mohr circle for three-dimensional state of stress, and we could get the state of stress. Any points in this circle shows the state of the stress, three-dimensional stress, and as alpha, beta, and gamma change, the sizes of these circles changes, and we get different values for the state of stress. Right. Now, in here, I'm going to show you state of stress, which is hydrostatic stress here. Okay, hydrostatic stress, sigma average is equal to sigma 1 plus 2 plus 3 divided by 3, or sigma x, x, y, y, z, z divided by 3. We call this I1. Remember, I introduced the invariance to you. And I showed you that if you use that coordinate transformation equation, Sn, we could prove that sigma 1, sigma 2, sigma 3, the sum of sigma 1, sigma 2, and sigma 3 is equal to sum of sigma x, x, y, y, z, z, or eta xi and zeta. Different axes, different coordinates give the same values for the sum of the stresses, and we call those I1. So hydrostatic stress is equal to I1 over 3. Okay, so hydrostatic stress is an invariant because 3 is a constant and I1 also is constant. So that is very important. Here we can show that cos alpha, cos beta, cos gamma. In this, obviously, this is a cubic element, and we have this sigma all over the place, showing that the state of stress is hydrostatic. It means the stress is equal in all directions. So cos alpha is OB over OA, cos alpha, cos beta, and cos gamma. We could get these relationships very easily, and as you can see, cos alpha, cos beta, cos gamma are all equal. So it means alpha, beta, gamma are equal, and LMN are equal. So it means that in hydrostatic state of stress, the cosine ratios are equal, LMN, or alpha, beta, gamma. Okay, so in here, if we put these values LMN in this equation for m equal to L and for n equal to L, we put it in this equation, then we get 3L squared equal to 1, and L is equal to 1 over root 3, which gives cos alpha equal 1 over root 3. Obviously these are all equal, so alpha, beta, gamma are equal, and equal to arc cosine 1 over root 3, which is 54.74. So the hydrostatic state of stress, the cosine ratios must be equal to that. In fact, this line OA makes equal angles to all three principal stresses, or to the three axes of stresses. Okay, so that's very important for the hydrostatic stress.